Окей. Никита, меня слышно?
Да, вас слышно.
Нормально, да? Хорошо, тогда я начинаю. Okay, so today we have two themes. First of all, I would like to finish the subject related to large n limits of normalized characters, and then we will begin a new subject. So I recall this topic. So this is large n limits of GLM characters, I mean irreducible characters. So I recall the definition. Here the index lambda is a signature, and the irreducible character is given by this Schur type formula. And the problem that we will to discuss and finish today, the problem is to find all possible limits of normalized irreducible characters. So normalized characters are denoted by tilde, and the definition is here. We divide the character by its dimension, which is nothing else than the value of the characters at the points 1, 1, 1. And we assume that our signature varies together with capital N and goes to infinity. And we want to understand what are the possible limits of these rational functions, or actually Laurent polynomials. So we expect that the limit will be some function on the torus. In fact, we take, I recall, we take the infinite product of unit circles. This is our infinite dimensional torus, and we take some part of it which consists of sequences of variables u1, u2, and so on, which are finitary in the sense that almost coordinates are equal to 1. And we expect to get some function in the limit, which is a function on this finitary part of this torus. Now I recall what I need. Maybe it's better. So I recall that a signature can be viewed as a pair of two Young diagrams, lambda plus and lambda minus, which are responsible for positive and negative coordinates. So the only restriction of this pair is that the length of one and the other in sum does not exceed the capital N. So the picture is as follows. We assume that our signature looks as follows. First, we list the row length of lambda plus, and from the other end, we list the row length of lambda minus in the reverse order and with sign minus. And in the middle, probably we have some numbers of zeros if necessary. So this is the picture which shows how to represent our signature as a couple of two Young diagrams. Next, to study the limit, you need some larger space. This larger space will be denoted by capital omega, and this is a subset of a long direct product. First, we have two infinity copies of R, actually of R plus, one next variable here and here. So in sum, we have six objects: alpha plus, beta plus, delta plus, alpha minus, beta minus, delta minus, where the alphas and the betas are infinite sequences of non-negative real numbers, which I assume to be weakly decreasing. Next, the deltas are simply non-negative real numbers, and there are two conditions. Essentially, three conditions, because one is for the plus sign and the other for the minus sign. And the condition is that the sum of the alphas and the sum of the plus the sum of the betas does not exceed the corresponding delta. And the second condition, its meaning will become clear shortly. Now, for any fixed n, I define an embedding of the discrete set of signatures into this set omega. To do this, I recall the notion of modified Frobenius coordinates. Actually, we can consider even ordinary Frobenius coordinates. It's not very important, but nevertheless, let's deal with modified Frobenius coordinates. So each of our diagrams, plus or minus, is represented as the couple consisting of the modified Frobenius coordinates alphas, A and B, sorry. And next, we normalize them. To define this embedding, we need some scaling, some normalization. So we set the alphas, plus or minus, are obtained by scaling the A coordinates. And I recall that there are finitely many of these coordinates. Their numbers is equal to the size of a Darcy square. But here on the left, we have infinitely many coordinates. So we adjust these finite sequences by zeros. And the same for the betas, which reflect the normalized B coordinates. And next, we normalize the size of the diagrams. In this way, we get a point here, a point here. So this is the picture which shows what we did. So we consider these two diagrams, and these are the A coordinates, and these are the B coordinates, and then they are normalized. So we have this obvious relation, and it leads to this one. Actually, we have here equalities, by right inequalities. And this relation comes from this relation, this relation comes from this one. So because the sum of the B1 minus and B1 plus can't exceed n. And this is reflected by this relation. And I denote the image of our of our signature in this space omega by this symbol. This symbolizes the scaling of the signature. And now the theorem is as follows. So assume we have a sequence of signatures and take the corresponding normalized characters, and a limit of such a sequence exists if and only if the corresponding points in our space converge to some point omega, small omega. And next, the limit function on this finite torus has a surprising simple form, elementary form. First of all, it is a product. It factorizes with respect to the coordinates. There is some function, capital phi, which is given by this long but totally elementary product. So this is a function in one variable u, which is assumed to live on the unit circle. And this is given by this expression, which assembles all our coordinates, the alpha and beta plus, And gamma, I explained what is gamma. As before, gamma is kind of defect, the difference between this quantity and this one, which by the very definition is a non-negative real numbers. So why this is surprising? Look, before the limit, the character is not very complicated, but still it's some special functions in a certain sense. It is given by a certain determinant. It's not an totally elementary function, but in the limit, we get a totally elementary expression. In some sense, it is more complicated because there are infinitely many variables here after the limit, but in the other sense, it is more elementary. It's not too surprising because it often happens that after a limit, after some asymptotics of certain, say, special functions looks simpler than the pre-limit expression. But still, it's very surprising that we get such an explicit expression in the limit. The proof, I will not give a detailed proof. It's not too simple. So this is the reference. This is the reference. Actually, in this reference, we are dealing with more complicated objects, a certain deformation of the Schur functions of the characters, the so-called Jack normalized Jack polynomials, but it's not difficult to extract the result related to the characters. But I would like, before finishing this theme, I would like nevertheless to show you, to emphasize some main steps, some ideas of the proof, because here we need the material that I tried to explain before. So assume I will explain only some part of the proof, namely, go in one direction. Assume that this sequence of signatures is such that the limit does exist. So it converges to some point omega. What we need to prove? We need to prove that for any m, any natural number m, any by fixed, we have convergence on the fine dimensional torus of this dimension. So what we need to prove? We take only m coordinates. The remaining coordinates are set to be ones. So we restrict the normalized character on this torus. We assume that n is large, so it exceeds this fixed m. And then in the limit, in the expected limit, we also have only m factors, because if we substitute the coordinates equal to 1, then look at this expression. If u is equal to 1, then the whole expression is equal to 1. So from this product, it remains only m factors. So we have to prove, we want to prove this limit relation. Then the idea that I already discussed is that instead of proving this as a convergence of continuous functions on a torus, we want to pass to some infinitesimal version of it. So we want to prove the convergence of Taylor expansions at the distinguished point 1, 1, 1, 1. The convergence means coefficient-wise convergence. So we have, this is our assumption, and the conclusion is we have a coefficient-wise convergence of Taylor expansions in m variables. This means, more precisely, this means as follows. We need to fix some coordinates and we take very simple coordinates. So the coordinate in the neighborhood of 1 is obtained just by adding some auxiliary coordinate t. So 1 plus t1, 1 plus t sub m, and 1, 1, 1. So the new coordinates are the t coordinates. So we take this function. This is a rational function, so we can take, and it assumes value 1 as t is equal to 0. So we can take the Taylor series on the left, this one, and likewise we substitute the same t in this formula, and we take the Taylor series, and this is also a good function, so there's no problem. And we want to prove the convergence of the Taylor coefficients. Next, the next step, as before, as I tried to explain, the next step is to replace the Taylor series by a series in the Schur polynomials. And this is reasonable because what we have on the left and on the right are symmetric expressions with respect to this variable. So we can re-expand this Taylor series as some series on Schur polynomials. So I recall these are the Schur polynomials. So we want to write this as a series on Schur polynomials. And I recall that we know how to do this. This is our binomial formula. It says that on the left, the part related to the normalized characters have such a form. So mu is a arbitrary Young diagram. I recall that these are no signature here. These are polynomial functions, which is reasonable. So these are series on Schur polynomials. Mu is a Young diagram with at most m rows. And this guy is some relative of a Schur polynomial, the shifted Schur polynomial, evaluated at our signatures, but this is signatures. These coordinates can be positive or negative. So this is what we get on the left, this series. So quite, and this is the factorial, the falling factorial power of degree, which is equal to the number of points of a number of boxes in the diagram. I recall this is the binomial formula. This is on the left. On the right, the part related to this expression is as follows. This is some general trick, a simple trick, how to expand a multiplicative expression on Schur polynomials. So we have some product of series. In fact, we can take any series, any even formal series, if you know its coefficients. So assume that we know the coefficients. This is my notation for the coefficients. Then we can get the expansion on Schur polynomials as follows. The coefficients are composed from these Taylor coefficients in this way. And recall, this is exactly the way that we see in the Jacobi-Trudi formula for the Schur functions. This is not accidental. This formula can be, the Jacobi-Trudi formula can be deduced from the Cauchy identity, which is something just of its type, of this form. Now, what we get, what we need to prove now. So there are no series. So what we have, we fix mu, which can be arbitrary. And this is our assumption. And we want to prove something related to the asymptotics of the shifted Schur polynomials. So our big problem is related, is reduced to this combinatorial problem. Show that we have such a relation. So I recall what is this. Here we have a shifted Schur polynomials. The arguments are the coordinates of a signature. The signature varies as n goes to infinity. It varies in a certain way, just in the way such that this object converges to some omega. Given omega, we have this series. And from this series, we can extract its Taylor coefficients. And this expression is here on the right. It is formed from these Taylor coefficients. And the next step is that actually this can be reduced to a particular case which is related to the case when m is absent here. This m is equal to 1, actually. One can reduce using what is here, what is needed here. Here we use the fact that this object is it's an element of an algebra of shifted symmetric functions, and this algebra is filtered, and the associated graded algebra is the algebra of symmetric functions. And so up to some lower degree terms, this object is essentially the Schur functions. And for the Schur functions, we have the Jacobi-Trudi formula. And the Jacobi-Trudi formula is just of this type. And using this observation, we can reduce it to the particular case when capital M is equal to 1. The Young diagram is simply one row diagram. The shifted Schur polynomials is the shifted analog of a complete homogeneous function. This is H star. And we need to prove this under our assumption. The following asymptotical relation holds. This expression converges to the coefficient, to the Taylor coefficient of this series. Now, the next simplification is as follows. Recall that our signature can be viewed as a couple of two Young diagrams, and assume first that which diagram is empty, so there is no negative coordinate. And assume that we can prove this relation in this case. Then it turns out that a certain trick can reduce our general problem to this particular case. So actually, one can simplify the problem by assuming that there is no negative coordinates. So in this case, we can treat our signature simply as a Young diagram which varies with n. And then this object becomes a function on Young diagrams, and we know that this is an element of our algebra of polynomial functions. And then the result that we need is essentially the one that I tried to describe previously. So this is the end. This is the end just of my sketch. I would like finally to emphasize the key ingredients of the proof. This is first the binomial formula, which is a new look on characters. Essentially, it is really a new look because people during many, many years worked with characters and proved many, many different formulas, but it turns out that one gets some very interesting combinatorics and very useful one if you look at the Taylor expansion of the character, which is given by the binomial formula. turns out that this is indeed a good tool, very useful. And the second ingredient is that we know well what is this algebra of polynomial functions. We have various realizations and we can play with them. So these are the two key ingredients of my proof. Okay, so now we abandon this theme and we pass to the next topic. Sorry. This material is more standard now, classical groups and their characters. So I would like to explain some standard material, but my point of view here is to emphasize the picture which is closely connected to classical groups. So there are two viewpoints. One can deal with some general theory which holds for arbitrary semi-simple or simple algebras and groups. And on the other hand, we are interested specifically in classical groups. And it seems to me that it is very useful to switch from one picture to another picture. So in my talk, I would like to emphasize the second picture, which is related to specific properties of a classical group. So first of all, what are classical groups? The general definition of classical group holds for arbitrary fields and even division algebras, but now we are interested in complex classical groups. The key fact is the following. Over the field of complex numbers, all non-degenerate bilinear symmetric or skew-symmetric forms, this is my notation for such a form, of a fixed dimension are equivalent. So there is, in each dimension, there is essentially one symmetric form and one skew-symmetric form. But of course, skew-symmetric means that the number of variables should be even. Now the definition is as follows. What I mean by a complex classical group. This is either the general linear group, so we take some complex vector space of finite dimension E, and GL is the group of all invertible operators on this space. Or sometimes people prefer to deal with the special linear groups, the elements with determinant equal to 1. And this is type A objects. And the type BCD objects are related to a form. So we fix a form. I emphasize again that essentially there is only one such a form. It's unique. And take the subgroup in GL, which consists of the operators which preserve this form. One can say the group of isometries of this form. And in the skew-symmetric case, we get the symplectic group, which is connected. In the symmetric case, we get the orthogonal group, which is not connected. And we prefer to take the connected component of a unity. So the notation is as follows. In tape A, we take either this or this. In tape C, I put it first for some reason. People usually say B, C, D, but in some sense, it is better to say C, B, D. We will see why. So this is the symplectic group, which preserves a skew-symmetric form, or sometimes people say symplectic form. And the odd orthogonal group, SO means the determinant equal to 1, or the foo orthogonal group in type B if a dimension is odd, and the similar objects which are of type D if a dimension is even. What next? So any such group, G, is a Lie group. And moreover, it is a complex Lie group. So it has a structure of a complex manifold. And by representations of this group, we mean finite dimensional complex representations, which are complex analytic. What means complex analytic? A representation is an operator function. So maybe it's better to. So representation T. Oh, ho, 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 ho. What is this? Sorry. T is a map from G to some space. So G is a complex Lie group, and this is also a complex Lie group. So this map is complex analytic. This means complex analytic representations. Here I use another notation, sorry. So assume T is some representation of our group, and we assign to it its character. In the usual way, we take the operator corresponding to G and take its trace. By the very definition, it's a class function. It's constant on conjugacy classes. And there are some standard claims which can be found in any good textbooks. Maybe it's better to list some textbook. So there are many good books. For instance, Fulton Harris. There is also a good manual by Daniel Bump. And what next, for instance? I also recommend, I like very much Zhelebenko, Compact Lie groups and their representations. What? About Lie algebra aspects, there is a book by Humphreys. But of course, we also have, while it's a classic, but difficult to read, also there is some book by Goodman Wallach. And so on. There are some other, also some nice little book by Jean-Pierre Serre about the algebras. Okay. So a whole collection which can be completed. So what we need? I don't want to prove this because this is more or less standard. So any representation is completely reducible, which means that it is a direct sum of irreducible representations. Any representation of our class is uniquely determined by its character. So for some problems, we can forget about representations and deal with their characters. Representation is an operator valued function, and the character is a scalar function. So it's it's a simpler objects. So there is a great advantage to dealing with characters and not with representations. Next, what we need. So assume that we take a connected version of G. So not a full orthogonal group, but a special orthogonal group. And denote by this symbol a subset. I will call it the set of regular elements. These elements which have no multiple eigenvalues. We are dealing with some matrix groups, so we can consider their eigenvalues of these matrices. And the subset of regular elements is an open subset which is dense in the usual sense with respect to the usual topology. And the conclusion is that our character is uniquely determined by its restriction to this subset. And note also that this subset is invariant with respect to conjugation. So it consists entirely of conjugacy classes. Next, we need the maximal torus in our group. It is obtained as follows. But in the case of GLN, it's very simple. We just take the diagonal matrices. What to do in type CBD? In type CBD, we need a form, a bilinear symmetric or skew symmetric form. Any such form can be written as follows. So I assume that Xi is a column vector here. Eta is also a column vector, but we transpose it. So we take this multiplication, row vector, matrix, column vector, and the result is a number. This is just the definition of form. And there are many possible variants how to choose this matrix. Sometimes people want, for instance, in the symmetric case, take for M the diagonal matrix. Sometimes it's convenient, but sometimes it's not. In our situation, it's not convenient. And we need some more sophisticated choice. So this, what we do in type C, we take the skew-symmetric matrix of such a type. The ones or minus ones are on the second diagonal. Here again, in the type B and D, we also use only the second diagonal, only the ones, because we need the symmetric matrix. This is the odd case. So we have this row and column in the middle. And this is the even case, the case of type D. The analog of diagonal matrices is obtained as follows. Here we have a symmetry, U1 and so on, and the same variables in the reverse order and inversed here. This happens in case C and D because we have an even number of the order of a matrix is even. In type B, we need one auxiliary element here, and it is equal to 1. Okay? So in this way, we obtain the maximal torus, which is a subgroup, which is isomorphic. Which is isomorphic to the product of m copies of the complex torus. The complex torus, we we replace the unit circle by the punctured complex plane. The result is called the complex torus. The next claim is as follows. If our element is regular, then it is conjugated to some element of a torus. So this is some linear algebra, some claim from linear algebra.
Sorry, what does it mean conjugated?
Conjugated, so G conjugated, I mean, so orbit, or if you, okay, I can write it directly. This means that there exists some H in G such that...
Сопряженный.
Да,
да, понятно.
Да. Exactly. So the conclusion is that we can restrict our character to the torus, and nothing is lost. No information is lost. The next topic is the while group. The while group, the definition is as follows. We take the normalizer of our torus in the group G and factorize it by the torus itself. So this is, by the very definition, it's a normal subgroup here. So we take the quotient. This quotient is a finite group. What is this? This is the picture, the structure of a while group. In type A, this is simply the symmetry group, which acts by permutations of its variables. In type C, this is the so-called hyperoctahedral group, the group of symmetries of an n-dimensional cube. It is a semi-direct product of a symmetry group and the product of n copies of a group Z2. What are these elements? They act by permutations, and these elements act as inversions because here we have a larger group of symmetries. The eigenvalues come in pairs. If you have some eigenvalue u, the symplectic matrix has in its spectrum also 1 over u. Okay. So this is some large group of symmetry. So these subgroups is generated by these inversions. In type B, the situation is exactly the same group here. But the type D presents some more subtle structure. Instead of this group, we have the index to subgroup of this one. So we have still the permutations, which are arbitrary. But this subgroup, by definition, consists only of only even number of inversions. This is very important. How to see this? This is actually seen from this picture. From this picture. It can be seen, but we can get only even number of inversions. It's a useful exercise to understand this little phenomenon. Okay. So what next? A very important proposition which says, so assume that T is a representation of our class. So a finite dimensional representation, which is complex analytic, and take its character and regard it, restrict it on the maximal torus of a type that I explained. and regard it as a function in coordinates with coordinates u1, un. What we get? We get some Laurent polynomial first. Second, this Laurent polynomial has only integer coefficients, so we can deal over the base ring Z. And finally, it is invariant with respect to the while group. In the type A case, the case of GLN, we already discussed this. And what happens? I will try now to explain why, for instance, why we have integral coefficients and why we have invariance. Okay, invariance is simple. Invariance is simple. It follows just from the very definition of this. Here, I would like to emphasize one point. In the case of type A, this while group can be embedded into G because this is the symmetric group, and we can just embed it to any permutation. We can associate, we can assign to it the corresponding permutation matrix. Okay. So in this case, we have an ordinary embedding. But in general, it's not possible. It's not possible. One cannot realize the while group in general as a subgroup in the corresponding complex Lie group, but it's not important. It's not important, and it still implies this claim, this invariance, because if you have a character, say you have a character, and we know that we have this relation, and we have implement the action of arbitrary element of a while group as conjugation with an appropriate H taken from the normalizer. And then because we have this relation, we obtain this invariance. So this is trivial. This is trivial. Now I would like to introduce some extra notation and explain the integrality relation. We need the very important notion of the weight lattice associated to our group. So I recall that the structure of our maximal torus, it's just of this type. And here again, one can use the term character. But here the character is understood as in relation to the torus. A character of the torus is a morphism to this group. So this is essentially a complex analytic multiplicative function on this group. And it's called a character. And what are the characters of this object? It's easy to see. It's some exercise. If you did not pay attention, just take it as an exercise to show that any morphism, any character of a torus has this form. So this is my notation for the element of a torus. A mu here is an n-tuple of integers, an element of this lattice. So this is my shorthand notation for this product. So we take as P the lattice, the n-dimensional lattice, but one can view it as a dual group in a reasonable sense, as a dual group to this one. So this is a dual group. And there is a natural pairing between this group and this group which is expressed by this formula, given one element and the other element, we assign to it a number. This is the number. So we have some map. This is a pairing between two objects. And this is by definition the weight lattice. So each mu is called the weight corresponding to our group. In our situation, the weight lattice is the same. For all our groups in question. But now, character now of our group G always has such a form, a finite linear combination of the torus characters with some integral coefficients. Why? Because we can restrict our representation, the representation corresponding to this character, we can restrict it to the torus, and then it splits into a direct sum of one-dimensional representations, because the group the torus is commutative, and in any component we have some character of a torus, some character, but there are in principle some multiplicities, which by the very definition are some non-negative integers. So we have this formula, and this explains now why we have this fact, why our series has integral coefficients. Okay, next we need the notion of the so-called dominant weights. The dominant weights form some subset of our lattice, which is defined as follows. Okay, of course, there is some general definition which holds for arbitrary semi-simply algebras, but I would like to explain it directly in some elementary way. So in type A, we need this restriction. We impose this restriction, which is essentially, this is just the definition of our signatures. So these are some analogs of this definition in the case C, B, and D. C and B is the same. We require additionally that all these numbers are non-negative. Here we don't have this restriction, but here we have to impose it. And in case D, there is something interesting. At the last coordinates, we have this inequality. So the last coordinate can be negative. This is some specific feature of type D. Why? This is just related to this fact. So the set of dominant weight is exactly a fundamental domain for the action of a while group in this lattice, on this lattice. So what means fundamental domain? This means that any element of a lattice can be moved to this subset under the action of a while group. Any orbit intersects this set and exactly at a single point. So because in type D, the while group is a bit smaller, we get as the fundamental domain something which is a little bit larger, because here this restriction is weaker than this one. So this is an exercise just to check that this is indeed a fundamental domain. But actually, in type B and D, the definition of the weight lattice it's not exact. The reason is that there exist the so-called spinor groups, spin group, which are two-fold covering groups of the special orthogonal groups. Okay, so here, for instance, if n is equal to 1, it's this is some specific case. Anyway, this group exists, but in small dimension, it's not true that these two-fold covering groups are universal covering groups, but essentially it's true for almost n. So these are already simply connected to groups. Okay? So what happens now? It happens now that the true definition of the weight lattice, which is applicable to the spinor group, is obtained as follows. We have to enlarge a little bit our lattice. I denote it by tilde. We have to add the shift of the lattice by this vector, which just means that the coordinates are either integers or they are all half integers. So this is the true definition of the weight lattice for the orthogonal Lie algebra. One can say it so. So this is the true definition. We will see why this is useful to use this lattice. But we will deal exclusively with the orthogonal group and not the spinor group. The next definition which I need is the roots. So I recall, I would like to, I forgot to say, sorry. So the weight, mu, which really appear here, are called the weights of our representation, which corresponds to these characters. So there are only finitely many of them because the representation is of finite dimension. But now I come to the notion of roots. What are the roots? The roots are some particular case of weights which correspond to a particular representation, the so-called adjoint representation. The group acts on its Lie algebras. The Lie algebras just affords some representation. It is called the adjoint representations. It has some roots, some weights, and these weights are, which are non-zero, excluding the zeros, are called the roots. So the roots can be positive and negative. So there are some general definition, but I would like just to give concrete description. So this is the adjoint representation. The group acts by automorphisms of its Lie algebras. So I will need the R plus. The R minus is obtained just by multiplying this by -1. So in type A, the roots are as follows. Here the epsilons are the standard basis of our lattice, the natural basis. So epsilon 1 is the vector 1, 0, 0, 0, 0. Now, in type A, the roots are as follows. The differences, and always I assume that I is less than J. In type C, these are as follows. In type B, almost the same by there is no factor 2. And finally, in type D, we have this. I would like to explain shortly how this appears, all this picture. So look at this picture. This one, I'm sorry. I need the picture related to this picture, this one. So what is the Lie algebras? The Lie algebras consists of a matrices of such a type with a symmetry related to the reflection about this diagonal. In the C case, in the case of type C, in this block, we get matrices which are symmetric with respect to this diagonal. And this is the source of the roots 2 epsilons, because this matrix units just produces some eigenvectors of a joint representation. Okay. In this case, we get, this is the source of the epsilons without the prefactor 2. But this does not give us anything, because here the condition is skew symmetry. So in Lie algebras we have zeros here. And finally, in type D, we still have skew symmetry, and we don't have this possibility. This explains, this is the source of this picture, So these are the roots. I don't want to explain exactly what this means. Just understand this in this dogmatic way. But in the textbooks, we can read the general definition of the roots. We need the fact that the set of roots is W invariant. This makes a sense, because what we have, the W, this the while group, it operates on the torus, and these objects lie in the dual object, in the dual group. So there is a natural dual action of a while group on the weights, and in particular, this makes sense to say that some subset of weights is W invariant, and this just happens for the subset of the roots. Next, we have a fundamental object, which is called the while denominator function, or simply while denominator. Why denominator? We will see. So this is the formal definition. So what we have to take, we have a product of all the roots. So in particular, one can take here if alpha is equal to, so then this object is the following. And so on. If you have plus, then you have plus and plus, and so on. So this is the definition. We can say, okay, but it does not make sense, because we raise this variable in some power, which in principle can be not an integer. So if you want, one can be a bit more precise and exponentiate. So represent our diagonal matrix or our element of a torus as an exponential of its Lie algebra. So just take, just put so assume that we have this. Now it makes sense this is just the ordinary product, inner product in Cn. And this expression takes this form, so no problem. Of course, it's a function, it's a multi-valued function. At first glance, it's a multi-valued function, but actually it's not. Why? Let's explain this. This is a very important definition. The half sum of the positive roots. I will explain how it looks concretely. But just take this as a definition and look at this formula. Look at this formula, and we can rewrite this formula as follows. Now the whole ambiguity is concentrated here. It's concentrated here. So this is, in principle, a multivariate function, but it's not. This is not. It's defined correctly. So now just let's examine this row. So what is this row? In type CBD, it is written as follows. We take this sequence and add epsilon, which is 1, 1/2, and 0. And this is why I put C first, not BCD, but because it just corresponds to this picture, 1, 1/2, and 0. I'm unable to rename this series, but instead of this, I just write it in this order: C first, then B, and then D. And in type A, it looks as follows. Row is follows. So we see that only this, excluding this one, type A is something separate. For CBD case, only type B presents some ambiguity, because in this case, we have integral coordinates, but still 1/2, 1/2, 1/2. So in type B, you have to give meaning to this expression. What is this? This is a two-valued function. This is a two-valued function on our torus. But it is correctly defined on its two covering, which is just the maximal torus in the spin group. So actually, all is okay if you pass to the spinor group. But we will see that in some formulas, this ambiguity disappears. So essentially, there is no problem with this ambiguity. Let's go further. Now we need the compact forms. So far, we were dealing with complex groups, and now we want to use also compact groups. The reason is that some features of the theory becomes easier if we are dealing with compact groups. We will see shortly why. So what are this K? This is the so-called real form, which is a compact. Its Lie algebras is a real form of a Lie algebra of G. But concretely, absolutely concretely, In type A, we take the unitary group. In type C, we get this group, which is defined as the intersection of our complex group, the symplectic group, with the unitary group in its standard realization. And I use here the standard realization, standard in the sense that I explained with this matrix along the second diagonal. And likewise in type B and in type C. So this is one possible definition, which is very convenient for all questions related to roots, weights, and so on. For instance, why it is? Because here we can take the intersection, can take the intersection of our torus with our compact group. And then our torus, which is as follows, it becomes just the compact torus, the product of n copies of the unit circle. So it's very convenient, this realization. But I would like to observe that there is an alternative definition, which in some situation looks more natural. Namely, we have in our disposition only three fields: the reals, the complex numbers, and the quaternions. Take the m-dimensional, finite dimensional space over this field of skew field of some dimension, say m, and there is an inner product which makes it, this space, a finite dimensional Hilbert space, one can say, of finite dimension, but still a Hilbert space. So this is the inner product, and take the group of isometries of this finite dimensional Hilbert space over these fields. And the group of isometries is the orthogonal group, the unitary group, or the symplectic group. So the symplectic group, the compact symplectic group, appears in exactly the same way as the orthogonal group or unitary group, but only it corresponds to the base skew field of quaternions. If we don't have any other fields, so this explains why we have only these possibilities. Sometimes some people even use the notation, the common notation, as U of M, and someone can say R, C, or H. So with this option, we get orthogonal group, a unitary group, symplectic group. So this the very notion of symplectic is in some sense hidden here. In this definition, at first glance, we have no symplectic form. It appears in some more sophisticated way. So this is some alternative definition. I would like to repeat it. Is sometimes useful also, but I will not use it just now. Now, a very important classical result, maybe in some sense. Okay, I would like just to formulate it. So we take the compact torus. I repeat again, it is the intersection of a complex torus with our compact form. We get this object, the compact torus, the product of unit circles. And we need two probability measures. The Haar measure on the compact group, which is normalized. The total mass is assumed to be equal to 1, and a similar object for the torus, for the compact torus. So this is my notation. And the Weil formula says the following. If you have a good, say, okay, continuous, say, function on K, which is a class function, meaning that it is constant on conjugacy classes, then we get this formula. So what is here? So here we have integration of the sorry, this is, oh yeah, it's okay. This is the compact torus. We restrict our function on this object, on this torus, and integrate it against the normalized Haar measure multiplied by the squared modulus of the y denominator. One can say that this function, this measure multiplied by this function is the radial part of a Haar measure. So the situation is similar to this one. If you have the plane with the coordinates x and y, we can pass to the polar coordinates r and phi, and then the Lebesgue measure is equal as follows. So this is the radial part. The radial part of the Lebesgue measure. And so this factor R is just this. So this is some analog of this R. Okay? And the angular component disappears, because if you want to integrate a rotationally invariant function, we don't need it. So this is some analog of the polar coordinates on the compact Lie group. So this is a fundamental formula. And now a corollary. So assume we have two irreducible characters of G. Now, then we have this integral relation. We restrict them to the compact torus, take the inner product, the scalar product with respect to this radial part of the Haar measure. And the result is either 1 if the characters are the same, or 0. So one can say that the family of irreducible characters form an orthonormal family in the Hilbert space with respect to this measure and take into account this factor. This factor is also quite natural because here this function is W invariant by the very definition of the Weil group. So this formula is the source of the Weil formula for characters. I will discuss it in the next time, but I would like just to make this observation. So now I repeat it, the irreducible characters form an orthonormal basis in this space. This is a pre-Hilbert space, the space of W invariant Lorentz series. And with respect to inner product, the inner product is given here. Where to read this? For instance, one can read Weil. It's not terrible here. And for instance, one can read, if you want, bump. Maybe Fulton Harris, don't remember, is it well or not for this purpose, but this is good. And now finally, I would like to explain, this is a very useful exercise, which I recommend it to all of you, the precise form of this. So for people who like only the general theory, for them, this delta, the Weil denominator, takes only, they memorize only this definition. Sorry, this definition or this one, if you want. For them, for these people, they think only in this form. Okay? It's good. It's quite reasonable. This form is very useful, but it's also very useful to switch from this abstract definition to some concrete, something which is more concrete. So what happens in type A, C, B, and D? So in type A, it's essentially the Vandermonde determinant. And in fact, this is some analog of the Vandermonde determinant. According to my definition, this is not exactly this, we have to multiply by something like this. But actually, in the definition of the characters, it's possible to get rid from this factor. We will see why. But now we have three expressions, which just corresponds to the fact that the epsilon is equal to 1, to 1/2, or to zeros. So we have a Vandermonde in these coordinates, new coordinates, and these extra factors. Again, there is a little ambiguity related to this, but I already tried to explain that it's not very important. So just compute, take the formal definition, add the definition, combine it with the definition of the roots, their concrete form, and from this deduce this concrete expression. What next? Next is that this object is W skew invariant. What means skew invariant? We have some multiplicative, some one-dimensional representation, a character of a while group, the sign character, which is just a natural substitute of a permutation character or sign character of the symmetry group. And look what happens. What happens here? If you permute the coordinates, then you have a skew symmetry, which comes from the Vandermonde. Okay? But we also have some skew symmetry related to the inversions here. But it disappears here for the reason that here the while group is a little bit smaller, and we have only the restriction of having only even number of inversions. So this skew symmetry disappears. So the sign characters is as follows. So I recall that the while group in the CBD case, in the C and B case is the direct product, it is the semi-direct product. So the sign character is the usual sign character on the symmetry group, and the characters on this group, which assigns to each inversion the minus sign. Okay. But in this case, in the D case, we have a smaller group, a little bit smaller group, and the sign character is trivial on this component. And now a fundamental fact is as follows. The sign character can be interpreted as follows. This plus minus 1 is in fact minus 1 raised to this power. This is the so-called length of the element of a while group. And the definition is as follows. The number of positive roots which turn into a negative root after the action of W. it transforms some, we have some partition with a set of positive root, and when we act on it by W, some part comes to R minus, and the cardinality of this subset is the length of W. And finally, we have this beautiful result due to, again, to Hermann Weyl, which says that our function, which is its definition, it's a multiplicative expression. It is equal to some additive expression, actually. The sum over. We take the half sum of positive roots. We apply W, which ranges over the Weyl group. We can equally well apply this to this element, no matter, this is the same. And what is this? This is some analog of the expansion of the Vandermonde. We, in type A, we can view the Vandermonde either as a product of differences, like this, or as a determinant which can be expanded. And this is just this analog. So this is a beautiful result. Where to read it? In any textbooks. But I think that the exposition in Golubenko maybe is the easiest one. So try, for instance, read Golubenko. I have no time to explain the origin of this equality. A good exercise is to prove this directly, just without any general theory, just take the explicit expression and try to verify this. So, okay, I have to finish. And next time I will discuss the Weyl character formula, which is some corollary of this material. And okay, next we will move further and further. Okay, so I can finish now. And just a moment, I will stop